Hi, welcome to Neuroverse, a podcast hosted by Carolina
and Clara, where we discuss all matters from neuroscience to philosophy and beyond.
Today's episode is on brain-machine interfaces or brain-computer interfaces. BCIs are known to decode neural activity in the brain, and they have primarily been used for therapeutics and rehabilitation of those that have paralysis or spinal cord injuries and other deficits in relation to movement. And I came across a few interesting papers that I would like to discuss.
Exciting. I think it's important to highlight the variety of different BCIs that exist. So BCIs can be categorized based on the signal acquisition method. So they can be basically non-invasive, semi-invasive, or invasive. So non-invasive methods would be like with scalp electrodes, like EEG recordings, where you put a cap onto the scalp, and semi-invasive methods would be using subdural electrodes, which are implanted under the skull and just on top of the cortical surface. And then finally, invasive methods would be using electrodes that are implanted deep within brain tissue. But BCIs could also be categorized by the way in which they use neural activity. And so this can be passive, active, or reactive. And these are not clear-cut categories. I mean, they overlap with each other. But passive BCIs basically just decode unintentional cognitive states, so like resting brain activity, whereas active BCIs would directly involve the user's voluntary intention to induce brain activity. So if a person was asked to think about moving their arm or think about something specific. And then finally, reactive BCI uses brain waves generated as a response to an external stimulus. So a stimulus would be presented and then the response to that stimulus would be detected. Basically all these different forms of BCIs can decode neural activity and also potentially feedback and developing therapeutics, as we'll talk about further in the episode.
Yeah, thanks for clarifying the different types of BCIs. It is really important to understand the differences. So I came across a few interesting papers while researching this topic, and the first one I'm going to talk about is one about high-performance brain-to-text communication via handwriting. So there already exist a lot of BCIs that can restore communication to people who have lost the ability to move or speak. However, there aren't that many that have been developed for more dexterous behaviors such as handwriting. Most BCIs for more gross motor skills such as reaching and grabbing and even point clicking with a computer cursor. But things like handwriting can enable faster rates of communication than just point clicking like specific letters. And so
do you mean that it will decode neural activity to produce a handwriting?
It will decode the intended handwriting activity. So
to carry it out for the person who's unable to communicate?
I don't think it's to carry it out. I think it's just to decode what the person intended. So if the person intends to write an A and imagines it, it can decode that A as opposed to like a computer cursor. Imagine going to point it and clicking on the A value.
Yeah.
A letter.
Yeah.
Mm-hmm. Yeah, so they developed an intercortical BCI that decodes attempted handwriting movements, so these imagined handwriting movements from neural activity in the motor cortex, and then translates it to text in real time using a recurrent neural network. So this imagined computer can then decode the handwritten letters that you're imagining in the brain.
That's super cool.
Mm-hmm.
Would you have to train the neural network based on neural activity during imagined handwriting?
Yes, exactly.
Okay.
And so they did this using specifically that and using key sentences and then training this recurrent neural network with the same patient several times, and then later on in the study they did the same thing with an unsupervised machine learning and compared the rates of accuracy. And just to cut to the chase, but then I'll talk a little bit in more detail, they were able to achieve typing speeds of 90 characters per minute, which is incredible.
Yeah, that's really fast.
Yeah, it's never been done before, and with a 94% accuracy. This was done during raw online accuracy, so basically in real time decoding the handwriting intentions. They also did the same thing offline with more finely tuned threshold type measures to be able to be more accurate, and they achieved 99% accuracy, which is amazing.
Wow. Interesting that the accuracy is mainly due to like the time pressure.
Yeah.
Yeah. But was this done in like healthy control participants?
This was done with a patient that has paralysis. The patient that they used had a high-level spinal cord injury and was paralyzed from the neck down, and his hand movements were completely non-functional. They had some twisting and micromotion, but not really discernible handwritten motion.
That's really amazing.
Yeah, essentially another intention for this study was that it's unknown whether neural representation of these highly dexterous motor skills still remain intact after these types of injuries, these high-level spinal cord injuries, whether it's a purely physical thing or if you also lose the neural pathways that lead to being able to do these dexterous movements. And this study has shown that no, these still remain, that you can still imagine handwriting and you can still decode this activity even though in a physical sense the person can't.
So out of interest, how did they actually detect the neural activity?
So they tested the neural activity using 2 microelectrode arrays in the hand knob area of the precentral gyrus, so invasive.
Okay.
And so then to actually try and characterize these handwritten letters, they use a time alignment technique which removed temporal variability, and then it allowed them to find consistent patterns of neural activity that were unique to each character, and from that then they were able to carry on with further experiments.
Yeah, I mean, it's so cool in itself that they were able to find patterns of neural activity that correlated to specific letters, because I don't know if that's been done before, but yeah, like
I don't think it has.
It's amazing what they were able to achieve and how it could help the patient, but also amazing how it teaches us about what neural activity means and how it can be useful.
And where it's stored.
Yeah, exactly.
So then they trained this recurrent neural network and used probabilities that could be thresholded to discern between characters. So they would just threshold the different characters, and that's how they would differentiate between them. And that's why the online processing was slightly less accurate, and then they would process it even further with an offline model using a language model, which I don't understand enough about to describe, but yes. Oh, and then afterwards, so after they were able to carry this out and get this high typing speed of 90 characters per minute, these were all prompted sentences, so they would give the patient a sentence and the participant would imagine each letter individually, and then the decoder would decode it and then retype it basically. But then they tested it in an unrestrained way so that the patient could think whatever they wanted, and they were still able to get a really high accuracy and 73 characters per minute and only an 8.5% error rate, which is, again, really quite good. And then they went on to theorize why potentially handwritten letters may be easier to distinguish from other strategies such as point-to-point movements, and as I've mentioned before. And they actually tested this theory by looking at time and how much time it would take to make these different movements and how they're more dexterous. And they found that writing out individual characters would actually result in larger movements, and these were 72% larger in comparison to straight lines or to these point-to-point movements, and therefore it made it less likely for a decoder to confuse the two.
Yeah, that makes sense.
Yeah. So it's interesting that in other approaches they were doing more point-to-point things, but these are actually harder for these models to decode and to be able to then understand.
Yeah, I kind of said this earlier, but I still find it super cool how much neural activity occurs in these motor regions when you're just imagining the activity and not actually doing it.
Yeah.
Like, it's amazing how, there's like theories that if you like watch a dancer dance, you're actually, well, it has to do also with mirror neurons, which we spoke about in the last episode, and how you're like imagining yourself actually moving in that way.
Yeah.
And so it would also influence motor cortex activity.
Yeah, and also when you think about when you write letters, there's some characters take more or less time, and this time-to-time variability, it also helps
to decode
exactly
the different letters. Yeah,
it's cool.
It would be really interesting to do that in Chinese, because each character would involve like a number of different strokes, so it would be a bit more complicated because you'd have to know when the like characters start and end, but it would technically be easier to decode each character because they're even more different than each letter in the English language.
Yeah, that is true.
And plus, I mean, that applies to other languages too. It's just what's familiar to me, but like,
One thing they did mention is they didn't do it in cursive because the cursive would have made it basically impossible for the decoder, because you need to have the separation of the characters to be able to do it. Yeah. So that was the first paper, which I thought was super cool. And in terms of how far we've come along with BCIs, it's amazing the things that we are able to do and decode.
Yeah.
And so this brings me on to my next paper, where they're talking about walking naturally after a spinal cord injury using a brain-spine interface. This was more of honestly a more surgery and method and engineering focused paper, but I still think it's cool to mention just so we're aware of where we are in terms of BCI development. And so they basically developed these wearable motion sensors to detect motor intentions coming from the brain, and then so this was done by implanting, so definitely extremely invasive, these 64 electrodes over the sensory motor cortex, which collected electrocorticographic signals. And this is a processing unit that predicts the motor intentions and then translates these predictions into a modulation of epidural electrical stimulation. So basically they also then attached to the back, the dorsal root entry zones of the spinal cord, another implantable pulse generator, which is connected to a 16 electrode paddle lead. So there's an implant in the brain and there's another one in the spine, and the one in the brain is decoding information of motor intentions and then stimulating at a high frequency, an ultra high frequency antenna at around 400 megahertz, and transferring these signals in real time to this processing unit in the back. And these stimulations then allow for movement to occur, which is how you go from having a spinal cord injury and being tetraplegic to then being able to start walking again using this wearable motion sensor.
That's crazy. It sounds like some really challenging surgical work.
Yeah, they have some cool cartoons where they show the cranial implants, where they basically open up the brain and attach these two like pads. They literally look like two pads on the brain. And then I don't even know how complicated the spinal attachment one is as well.
That's probably even more complicated because the spinal cord is like so sensitive. And, but I think, the invasive methods are like invasive for a reason. It's when the condition is so devastating that the benefits of the technology outweigh the risks.
Yeah, absolutely. These are in very extreme cases, and and with patients that want to undergo these trials, of course. But a cool takeaway of this paper was that anatomically intact yet functionally silent pathways from the brain can modulate the impact of epidural electrical stimulation on the activity of the spinal cord. And the challenges with this type of technology is, first, the stimulation parameters had to be finely tuned depending on the targeted muscles and the desired motor function. And secondly, the onset of the stimulation had to be precisely synchronized with the motor intention. That's another big challenge.
Yeah.
And then
it would be really annoying if you were like, move my leg, and then like
30 seconds later
oh, it's moving finally. Like, yeah.
And then again, finely tuned control over the activity of the muscles. But this wasn't just you implanted and the next day you're walking.
Of course. You need to learn how to kind of interact with the device as the user, right?
Exactly. And also you kind of need to learn how to walk again. So there was a figure in this paper which was showing the progression of someone walking. And the way that they actually did it is they didn't stimulate the actual site of injury. They would stimulate a little bit below it, and that would then cause the muscle to basically remember and then move, and then that would allow everything else to move over time as well.
Yeah. I think what I noticed is the key thing with BCI is also the patient's abilities to interact with it and like learn how to gain cognitive control of their neural activity, which is amazing. And I guess we don't really realize how much cognitive control we could have until it's demonstrated in ways like this. Yeah.
I think it's so cool.
So and when I was researching for this episode, what interested me the most was like the use of BCI for something known as locked-in syndrome, which is a really devastating, arguably the most devastating condition, where you have a fully functional brain, but you are restricted within a non-functional body. So you are alert and you're fully aware of your environment, you're taking in sensory information, but you have no output, you have no control over any like motor movement or speech. It can be caused by many different things, but it often occurs in the late stages of amyotrophic lateral sclerosis, or ALS, where patients progressively lose their motor control, and it can get so bad that patients can't keep their eyes open. And so as I was reading about all of this, I realized how challenging it is to come up with ways for these people to be able to communicate, but also how important it is and what a big difference it makes in quality of life. And so some of the earliest BCIs, well, it was in like 2010, there was a group that developed a BCI for home use, which I think is also important. Like in the context of all of this, you could come up with the fanciest thing ever, but if it's like restricted to a lab, it's not going to be practically very useful. So they came up with this BCI for home use for severely motor disabled patients, and tested it on one patient with advanced ALS. And this system was non-invasive, and it was based on EEG activity. So with EEG, you can record neural activity on the scalp in response to a specific stimulus, which is called an event-related potential. And then within the event-related potential, you can like extract different components of the event-related potential. And one of them that is commonly used is called the P300. P stands for like positive, and 300 is because it occurs around 300 milliseconds after the stimulus. So this BCI was based on the P300 component of when a patient was facing a video monitor and there was a matrix of 72 items, and then every 100 milliseconds, a different group of a few of the items would flash. And basically the patient was asked to like spell out a word. So say the 72 item matrix was like filled with letters, and they were asked to attend to their desired item. And then every time a group would flash, they would have to count how many times it flashes. And based on that, the computer could calculate the EEG response when each group flashed. So some of them would contain the item the patient wanted to select, and then the rest wouldn't. And it would compute the P300 and then determine, using a multiple regression algorithm, which item was the desired one. And then the contents of the matrix can be like customized by users. And or if you had compromised vision, then it could be made auditory instead. It worked, and it improved the patient's quality of life and enabled the patient to communicate better. And it's quite, like non-invasive, easy for home use, and not the most complex BCI ever, but really interesting that as someone who's also dabbled in EEG, I was really happy to see, because everyone seems to kind of think EEG is meaningless and doesn't mean anything, and it's recording from the scalp, and so it's prone to so much noise, which is all true. But to see that there's also something really effective that can come out of such a noisy kind of method is really cool.
Yeah, definitely.
And then as I read up more about locked-in syndrome, I came across a very recent paper where this group used a different technique with auditory neurofeedback training. And again, it was on a patient that was completely locked in, that was in the advanced stages of ALS. And throughout the study, his condition actually worsened progressively, so they had to continuously adjust their method based on this, which is how they came up with this final method, which is really amazing. So another method that's sometimes used is like eye tracking, so people will present someone with a screen and follow their eye movements to see what letters they want to select to spell out a word. But like I said, a lot of patients eventually lose control of their eyes, so they can no longer open their eyes or move their eyes. So in this case, what they did was a invasive BCI, where they implanted 2 64 microelectrode arrays that were each around 1.5 millimeters wide, so quite small, in the primary motor cortex and the supplementary motor cortex of the patient. And they asked him to imagine physical movements, which is often done in other people to control prosthetic limbs, but they were actually unable to detect responses when the patient attempted to imagine his hand or tongue or foot moving.
Oh, okay.
So in contrast to the study you've described, I think in this case it was even more challenging to find a way to read out neural activity that was meaningful. So then they provided the patient with an auditory feedback. This is just so amazing to me. But they basically recorded neural activity and then mapped the spike rate that they recorded to a frequency of an auditory tone.
That's cool.
Yeah. So, which, people do just for fun.
Yeah.
Create music out of neural activity. And so this is the neural activity that was happening in real time that the patient was then played back. And they basically trained the patient to modulate his neural firing rate to match an auditory tone.
Wow.
Which is so meta.
Yeah.
And this took a long time. It took around 90 days of trialing it. But this links back to what I said earlier of I don't think we've realized how much cognitive control we could have over our neural activity.
Yeah.
Because we're normally not just recording neural activity and trying to alter it.
Yeah.
And so he basically was then able to modulate his neural firing rate to play a rising tone or a descending tone that either signaled yes, rising, or no, if it was descending. God. And then he selected letters by using this auditory neural feedback to make phrases and words. And even though this took a really long time, it was a massive improvement to his quality of life, and his family as well. And by 3 months after implantation, the patient was able to use the system for voluntary communication. And so it shows, firstly, that volitional communication is still possible in a locked-in state, which is amazing, but also that this strategy could be used even though it takes a long time to train. And another limitation that was highlighted is that this particular patient had ALS that targeted motor neurons that travel from the spine to the muscles, but 95% of ALS patients actually have degeneration of the motor cortex, which would obviously mean this auditory feedback control probably wouldn't work because it involves cognitive control of your motor cortex neural activity. So it will probably not be applicable to most patients, but still very interesting technology.
Yeah, and such an amazing, demonstration of how we can have so much cognitive control over our neural activity.
Yeah, I think if anything, it was like a feat of the patient.
Yeah. Wow.
Yeah.
This paper you were just talking about leads in really well with my next one about in terms of cognitive control. And in this case, the focus was on a sense of autonomy. So the title was Sense of Agency for Intracortical Brain-Machine Interfaces, which I think is so cool because they recognize that, yes, there's been incredible progress with brain-machine interfaces, brain-computer interfaces, all of these different interfaces at decoding neural activity and maybe even stimulating and provoking movement. But what about agency? And how much of the movements that are carried out with the help of BCIs, how much do these patients feel that they do have agency or not? And so they did this study looking at congruency between motor commands and also looking at sensory feedback and also looking at whether they were focused on the primary motor cortex, and we know that it's involved with movement, but how much does it take into account sensory feedback as well, and in terms of updating it and how it helps us have a sense of autonomy. So they used this patient that was actually already quite familiar with BCIs, but this patient had reached a plateau in terms of the therapeutic progress that it was making, so wanted to go on to the study which had a focus on autonomy, and they were also investigating whether autonomy helped improve therapeutic outcomes.
Yeah.
And so what they did is they had a BMI that consisted of a 96-channel array implanted in M1, in the hand area of the left M1. And they also had this NMES system, which is a neuromuscular electrical stimulator on the arm or on the hand. And they instructed the patient to do an action, whether open the hand or close the hand. And when the patient did this, the BMI decoded the neural activity, and then they presented the patient with either a visual response, so they basically would show a hand next to the patient's hand that either did the same activity, so it was congruent, or didn't do the same activity, so it was incongruent. So basically, if the patient thought to open the hand and the video also opened the hand, then that would be congruent. And if the patient imagined opening the hand and they presented a video of closing the hand, that would be incongruent. And then they did the same thing with sensory stimuli, where if the patient imagined it was opening the hand, the neuromuscular electrical stimulator would fire so that the patient felt that it was opening his hand, and vice versa for incongruent. So the patient would imagine that it was opening his hand, but the stimuli actually made it feel like if he was closing the hand, then that would be incongruent. So they did this as a way to see whether the congruency or incongruency affected the sense of autonomy. And the conclusion was that yes.
But as in, what was the autonomy measured as? Was it like reported by the patient?
Yes, it was reported on a scale of, I think, 1 to 100.
But did they test, like you mentioned before, how more autonomy and congruency improved the implementation of the BMI?
So the question wasn't about the implementation of the BMI. The BMI was able to decode the neural activity perfectly fine, so, as in like previous studies.
Okay.
They were looking at whether or not somatosensory congruency was effective in driving a sense of agency, and they confirmed this. The results showed this. But then the additional question was whether or not it helped with therapy and improvement of their paralysis.
Oh, right. Yeah, yeah. And did it?
So they didn't mention I don't think they mentioned the result of the therapy because I think that was slightly outside of the scope of their paper. They were mainly just focused on agency.
Mm-hmm.
The therapeutic side would be more of, I think, was more of a future directions.
Yeah.
Maybe in the next paper, who knows. But yeah, I would also be curious to understand more about that.
Yeah. That's really, a really good demonstration because that's what I would expect. Yeah.
But yeah, I just thought it was cool that there was a paper that had a greater focus on agency and not just on outcome.
Yeah.
Yeah.
Because it's definitely important to take that into account as well. Like just in general, taking into account the patient's experiences, right?
Yeah.
And ultimately, like, these technologies can inform us about, like I said earlier, like neural activity and what it means and how it can be used. But ultimately, they are for therapeutic usage. And so that is bound to shape, like, what sort of things people create. Because it really depends on the needs of the patients. And everyone has such a specific, like, deficit in terms of motor disorders or locked-in syndrome.
Yeah.
So, and also this progresses over time, right? So there needs to be like different types of BCIs at different stages of disease or neurodegeneration.
Yeah, and I think it's also important, like this last paper, to show how accurate these BMIs are at decoding the activity, and also in terms of sensation and things, because maybe we think that they're doing a good enough job, but I think the fact that the congruency was highly related to a sense of autonomy shows that the job is quite good. And I also just wanted to mention that the first paper I talked about was by Krishna Shenoy's lab, who has passed away but did a lot of amazing work in terms of BMIs and decoding neural activity. And the second paper that I talked about was by Henry Lorak, and the last one was by Olaf Blank and Ali Rezai, who have labs in Ohio State University and also Lausanne in Switzerland. And I feel like the neuroprosthetics lab in Switzerland is super cool, and they're always doing like really cool stuff.
The one that I mentioned was also in a group between Tübingen and Geneva.
Ah, cool. Yeah. So, just to wrap up, super interesting to discuss the state-of-the-art brain-computer interfaces that we have and the amazing progress that has been done in the field, and also the incredible therapeutic uses that we have for them.
Yeah, I have to say I was pleasantly surprised by how advanced these technologies are, because I wasn't previously very familiar with the state of the field, but it was really cool to see what has been achieved and at what a fast pace everything is being developed at.
Yeah, and I think given that we're both more fundamental researchers, I always have quite a high level of skepticism when it comes to clinical papers and things like that, but it was really rewarding to reading about all of these applications of neuroscience into therapy and how effective it has been.
Yeah, because there aren't that many examples of applications directly from like basic neuroscience to the clinic. If anything, it's the things that work in terms of neuroscience clinically are not very well understood at the basic level. So this is a nice like basic science to clinical usage. Yeah. It's
amazing.
I hope you enjoyed the episode today. Feel free to follow us on our social media at neuroverse_pod on our Instagram and Twitter, and check out our website neuroversepod.com for more information and to find out more about all of the papers that were mentioned in today's episode.
Thanks for listening.
Thank you so much for listening to today's episode. If you enjoyed the episode, be sure to check out our Twitter and Instagram at neuroverse_pod, and for more information, check out our website neuroversepod.com. Thank you for all your support. We really appreciate it.